I just wanted to make an announcement. Today, there is a professor from TIFR in Mumbai, Professor Vivek Datar. He's a particle physicist who's working on the Indian Neutrino Observatory since 2015. He's visiting campus today and tomorrow. Professor Datar will be giving a talk on the neutrino particle and its relevance in terms of particle physics today and what it tells us about the beginnings of the universe, probably. And the students of class, physics students of class 11 and 12 will attend the talk. It's at 2 p.m. today over here in the senior audi. Classes 9 and 10 are invited to attend the talk. That means it's optional. You can take a call on this because of your exams and scheduling. Any other students from classes below that are also welcome to attend. So please be here on time, 2 p.m. seated, ready for the talk. There is also Professor Datar and his wife is also coming along. They are also bird watchers. So there is going to be a bird watching session tomorrow morning. All those who are interested, please get in touch with Reena about this. And we'll fix up the plan and then let you know. Thank you.
Good morning. Today I'll be talking about a very powerful and emerging field, which is nanotechnology. Now, before going into it, I'd like to mention that this is only an introduction to the field. Nanotechnology is very interesting but very complex, and my intention today is to talk about some of the core ideas of the field using analogies and examples without necessarily going into the physics or science behind nanotechnology. So let's begin. What is nanotechnology? Nanotechnology is a field that deals with particles at a very small scale, to put it simply. So how small? Well, sizes of 10 to the power minus 9 meters, which is extremely tiny. If you were to longitudinally slice a strand of human hair into 50,000 parts, the thickness of one of those parts would be 1 nanometer. So let's look at the sizes of matter. On one hand, we have objects of around about 10 centimeters, which is what you would call bulk matter. While on the other end, you have the atomic scale, which is 10 to the power minus 10 meters. Now, nanotechnology deals with particles of size around here, which is 1 nanometer, which is 10 to the power minus 9, to 100 nanometers, which is 100 into 10 to the power minus 9, 10 to the power minus 7, as you can see here. So, if a nanoparticle is neither at the bulk level nor at the atomic level, what really is it? And how could we intuitively imagine one? So, consider a lump of clay that you could grind down to fine dust. Have we got nanoparticles now? You could ask. Well, not quite, because there's something much more interesting that happens when you break down bulk matter into nanoparticles that has to do with the forces at play down at that scale. So consider what happens to gold nanoparticles in the citrus solution. Because of the forces at work, these citrus ions surround and attach themselves to the gold nanoparticles. And you can think of all these surrounding citrus ions as forming a kind of shield around the gold nanoparticle that prevents it from combining with other gold nanoparticles because all these surrounding shields repel each other. So this way the particles are kept isolated from each other and the nanoscale size, which is somewhere between 1 to 100 nanometers, is retained. So historically speaking, we've been experimenting with these solutions for a long time now. For example, we've been employing nanotechnology in processes like tire manufacturing that uses carbon black, and to even stain windows in churches using colloidal solutions of gold nanoparticles. But even though we knew how to create these suspensions, we largely relied on trial and error method to discover them. And the interaction at work in these suspensions were a result of the inherent properties of the system, like we saw in the case of the citrus solution, and not due to direct human intervention. There was some sort of self-organization at play. Now, if you look around, nature has mastered this technique of self-assembly to create a remarkable array of adaptive features. So let's see a few examples to better see how this self-assembly process is used. So my first example would be the lotus leaf. The lotus leaf has these tiny peaks on the surface, as you can see in the picture, that are uneven and have a specific density and spacing, and as a result forms a very enhanced water repellent layer. So this ensures that any water droplet that falls on the leaf easily rolls off, carrying with it any dirt or dust present on the surface. Now, this is important because since most of the stomata are on the surface, upper surface, and not on the underside, since it has to float on water, this self-cleaning mechanism is crucial to prevent any clogging in the stomata and ensures that respiration takes place normally. So my second example is Siphocalis beetle. So this beetle has a highly disordered thin layer of chitin, as you can see in the image, on top of its exoskeleton that appears a brilliant white, in fact whiter than any artificially produced white coloration. And this property helps it to camouflage from predators as it lives among white fungi. The third example is magnetotactic bacteria, which actually synthesize nanoparticles of iron oxide called magnetosomes and actually build a mini magnetic compass inside that they can then use for navigation to favorable habitats that have desirable levels of oxygen. So this is okay, but what are some of the ways in we can currently use nanoparticles given our knowledge and understanding of them? So one special feature of nanoparticles is the dependence of their optical properties on size. And this happens specifically in case of gold nanoparticles. So it turns out that when you break down a nice yellow lustrous piece of gold into nanoparticles, they're not golden anymore. The color that they exhibit depends on their size. So within a range, smaller nanoparticles appear blue, and particles at larger sizes in that range appear red. And this is why they could obtain those red and yellow solutions, colorations in glass, using gold nanoparticles in different sizes. So let's take a closer look at another such property that depends on size and how exactly we have been using it to our advantage. So remember, we're looking at sizes ranging from 1 to 100 nanometers. And now within that scale, gold nanoparticles exhibit very interesting changes as you change the particle size from 20 to 100 nanometers. Okay, so to understand this, let's do a thought experiment. Imagine yourself shrunk down to the nanoscale, next to these particles of different sizes, armed with torches. So if you were to shine a torch on nanoparticles of the smaller sizes, at around 20 nanometers, what would happen? Well, you would get back almost nothing. Almost all of their energy incident would be absorbed and dissipated locally as heat. However, if you were to move to a larger size particle at around 100 nanometers, if you shine the same torch, what would happen? Well, you get back a laser. It would scatter light of about 1,000 times more intensity than the incident light, than the torch you shone. And this heightened effect is caused by something called surface plasmon resonance. So, the electrons on the surface of these nanoparticles that you can see in the picture, they form a kind of cloud around these particles. And under light of certain wavelengths, these clouds start oscillating very rapidly with the same wavelength as that of the incident light, and this causes a very strong emission, intense emission to take place. So how can we use these various curious properties? So let's first talk about the smaller 20 nanometer sized nanoparticles. Now, I could use these nanoparticles to get rid of tissues in the vicinity of it. How? Well, just by shining light onto these smaller nanoparticles, they would dissipate almost all of their energy very locally and burn the nearby cells. And such a device, having such targeted and local effects, could be quite powerful in the field of photothermal therapy for burning undesirable tissues, for example, in the treatment of cancer. So, what about the larger size nanoparticles at around 100 nanometers? Let's see how we can use their properties of intensely scattering light in a biosensor that could be used to detect a particular target molecule. So here's a schematic diagram of the biosensor. So this part is the external circuit where I can actually detect a current that flows through it. Well, this yellow slab that you see, the gold surface, is the actual probe that is placed where we want to detect these target molecules. Now, this circuit has a nanowire that's coated with gold nanoparticles. And these gold nanoparticles are further attached to biochemical receptors that are seen in green here, that have a lock-and-key mechanism with the target molecules, which is shown in red here. The blue molecules are other particles that we're not concerned with and that don't lock with the biochemical receptor. So again, shrink yourself down to the nanoscale and imagine the circuit right next to you. Now, just with the nanowire and gold nanoparticles, without the green biochemical receptors and target molecules, if you were to shine a suitable torch on the gold surface, as we saw earlier, there would be a strong resonance and an enhanced oscillation of the electrons on the surface of these nanoparticles. And this would then trigger a surge of current in the nanowire that we could actually detect. So, when we add those biochemical receptors that have locked the target molecule onto those gold nanoparticles, if you shine the same torch, well, you wouldn't see the same surge of current as you saw before, because the size of the associated molecule has changed a bit. There is a shift in the resonant frequency that would produce that resonance and that surge of current. So you would have to change your torch and use a slightly different torch suitable to that associated molecule. That is the gold nanoparticle attached to the biochemical receptor that has locked the target molecule, to seize the resonance and the surge of current that you want. Okay. So once we have tested this in the lab and identified which torches or wavelengths of light work best for the whole associated molecule, and this would be specific for the target molecule we want to detect, we can actually use this device in an unknown setting, say the body. If we shine that torch onto the sensor, if such disease or pathogens are present and enough number of target molecules are detected, this would trigger a surge, a highly enhanced current that I can detect on my external circuit and confirm the presence of those target molecules. Now, this example is only a simple application to this approach. But this approach that is made possible by nanotechnology has very far-reaching implications for biomedical research, specifically cancer treatment, where traditional technology has not been able to find an effective solution. Considering there are most advanced techniques, advanced and used treatments are techniques like chemotherapy that are non-local, extremely toxic and not that effective. There is a need for viable early diagnosis, localized treatment. And this approach using nanotechnology offers a possibility of that. many of these applications are considerably impressive, the larger revolutionary vision of nanotechnology is molecular assembly, which is essentially the factory assembly line scaled to the very atoms and molecules. And this could possibly be the way forward for nanotechnology. But for now, we are not anywhere near that kind of precision or manipulation. What we're dealing with today is evolutionary nanotechnology that sort of aims at improving existing products and processes through nanotechnology. And for this, we have at our disposal very powerful tools that allow us to actually see at the nanoscale and also to manipulate atoms to an extent. So let's take a look at the instrument, the scanning tunneling microscope, in a short video.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on the surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
Nanotechnology is so powerful and fundamental that it will make an impact everywhere. Biomedical research where there is a need for localized treatment. The energy sector where we can actually tune the range of solar panels to absorb light in the infrared region and then can use that to utilize much more surface area, like we could use it on windows or tablets or anything else. The silicon industry, which uses extremely toxic chemicals at the moment to make to imprint the small transistors on this wafers. Material science, you name it. Because it's such a vast field, integrating knowledge from so many different sectors, I've only covered a few principles and their applications to give a glimpse of the possibilities that this field offers. So, I'll be ending by showing a short clip that presents a broad view of the current state of nanotechnology and its futuristic possibilities.
It turns out that the world with the really small is full of clever things we can use. The surface of a lotus leaf repels almost any liquid. A super close look reveals the secret. Tiny hair-like bumps that cause drops to roll right off the leaf. Maybe we can mimic this, making a coating to shield airplanes from ice buildup. Once, it was a mystery how a gecko could walk up smooth glass. Gecko feet are covered by 500,000 tiny bristles that branch into split ends, each with a pad on the tip. The structures build up an electrical charge that attracts them to the surface, adding up to incredible sticking power, and a model for a new kind of robot that could climb almost anything. A spider also harbors secrets. Spider silk thread is pound for pound stronger than steel, and yet completely elastic. Imagine what we might build if we could produce a synthetic version. The first step is getting a closer look at spider silk. The journey could take us all the way down to what we call the nano world. The silk is 100 times thinner than a human hair. On it, there's bacteria. Near the bacteria, 10 times smaller, a virus. Inside that, 10 times smaller, 3 strands of its DNA. And nearing the limit of our most powerful microscopes, single carbon atoms. 4 of them are the size of 1 nanometer. Welcome to the nano world. This incomprehensibly small place is the new frontier. Exploring it will lead to huge changes in our lives. Our most advanced microscopes can now see this. Individual atoms, though fuzzy, proving years of scientific theory, simulated here. And not only can we see them, with the tip of a powerful microscope, we can actually move atoms and begin to create amazing nano devices. Some could one day patrol your body for all kinds of diseases and clean up clogged arteries along the way. Tiny chemical machines of the future may even repair DNA. One of the wildest things about the nano world, substances here behave differently than the same material does in our world. To us, gold is golden in color. But nano gold can be any color. It absorbs light and generates heat, leading to an idea. Injecting nano-sized gold particles into the bloodstream, which are chemically coated to attach to cancerous cells. An incoming laser beam heats the gold particles, burning the cells. The promise of nano goes beyond medicine. Another material with far different nano properties is carbon. The same breakable stuff found in pencil lead. At the nanoscale, it is mind-boggling strength. With it, we've created the world's thinnest material, graphene, 1 carbon atom thick. It's harder than diamonds, but nearly as flexible as rubber. Turned into a roll, it's called the carbon nanotube, one of the strongest and lightest materials on Earth. With it, we could one day make things we can only dream about today. nanotubes to build an elevator to space. We are on the threshold of extraordinary advances, born of our drive to see all that's hidden in the world around us.
Are there any questions?
Why is gold so relevant in this nano?
Yes, actually, this is where a lot of complicated physics and maths comes into play while trying to explain why specifically gold at this particular size behaves that way. And I mean, it's all explainable using quantum mechanics and other models such as knee theory that explains the color of gold nanoparticles. But I decided not to cover that aspect because the complex technicalities involved.
So reactivity is not as reactive as other.
Could you explain in a simple way what biosensors do? That will be all that complicated.
Yeah. So basically, biosensors, this particular biosensor would be used to detect a certain target molecule that I want to confirm the presence of in an external environment of the body. So what I have is gold nanoparticles coated on this nanowire. So now, if I shine a torch or a light of a particular wavelength, there would be a strong resonance at a particular wavelength, to which I can detect, to which there would be a surge of current because of the enhanced oscillations, and there would be a surge of current that I can see, I can detect. So now if I attach biochemical receptors that will help me attract or detect these target molecules, if I attach the green molecules to my gold nanoparticles, this whole associated molecule would have a slightly different resonant frequency, to which if I shine light, there would be a surge of current which I can detect. So if I could place this probe inside the body or in an external environment, sorry, I'll just go back a bit. If I could test this in the lab where I know for sure that I have a certain percentage of target molecules, and that's sort of, I'm calibrating my biosensor to detect it, I could identify that wavelength for which it would respond, and then take it to an unknown environment where I don't know if these target molecules are present, and then shine that wavelength to see if there is a surge of current. So if there is, then I would have known that I have a number of target molecules attached to the biochemical.